With 3 plus, it's asking electrons. So 3 plus, that's going to be 18 electrons, because it has 3 more positive guys versus negative. So that means you have 3 less electrons.
Does it matter if we write the E for electrons like uppercase or lowercase?
Oh, no.
Okay.
You can change it up. Doesn't matter. I just, instead of writing out the word electrons, I just like to write it like that.
Alright.
Okay, the next one, you have to find the species with 10 electrons and 14 neutrons. So let's see if you're able to figure this one out.
It's A. Since the very first one, it was pretty obvious. The first one's 13, the second one's 13, the third one's 7, the D is 12, and E is 10.
Okay, notice I just put protons first, because that's going to help me figure out electrons and neutrons. It's based on protons, so it's best if I know those numbers. Now, it says it has 10 electrons. So, if I look at this, you have 13 here. If it has 10 electrons, it's going to have a 3 plus charge. So far A is working. What is wrong with B? There's nothing wrong with it, but what is it missing?
It's not missing any electrons.
Yeah, so that's an atom instead of an ion. So because of that here, the electrons will be the same. So this one's not going to work. If I look at the next one, I have 7 protons
That
with
would
a
be 7 neutrons.
3 minus. That means you have how many
10.
electrons? Yeah, 10 electrons. So if you look at this, okay, this is working out in the number of electrons. So let's just leave it at that. Let's go to the next one. I have here magnesium. Protons is 12. 2 plus electrons will be 10 also. Okay, so that's still in the running. Next one, you have 10 protons. It's an atom. Notice there's no charge to it, so the number of electrons will still be the same. So you still have the rest of them in the running. Now let's look at neutrons. Neutrons, notice they give you the mass numbers. So here, 27 minus 13, you will get 14. So that's the one that's so far checking out in both electrons and neutrons. So this one's working. Let's just look at the other ones, just so that we get practice. So here,
Same amount. Because it's all over the place.
well, B was out, so I don't even need to do B actually, now that I think about it. Let's look at C. So here I have 14 minus 7. Here I'm going to get 7 neutrons. That's not what I'm looking for. This one's out. Next one, 24 minus 12. So that's not going to work out. And then the last one is 10. Bam, that one's out too. So the only one that works is A. You don't have to go into this much detail, it's just practice, that's all. Because you should have noticed, oh, if the first one works, most likely that's the correct answer. Okay, now we're going to look at how those numbers are calculated. Remember, it's based on the isotope's mass and its percentage. So if I look at this one here, I have a hypothetical element. I'm just calling it HY, just the first 2 letters. Has 3 isotopes, meaning it has 3 different neutrons. the nucleus is slightly different. So I have the 3, HY 299, 300. Now these are the mass numbers. Now notice how they got these numbers. If you look at the natural abundance, here I have 5%, here I have 65%, and then here I have 30%. And it says the isotopes are 299.0, 300.0, and 301.0. So they're just using the mass to assign the mass number. Now, again, the actual percentages vary. Now, if I look at this, I need to figure out the atomic mass of this hypothetical element. Now, if you had to just make a guess, the number should be close to which one of these 3?
300.
300, because notice 65% of it exists as HY 300. So majority of it, over 50%, has that particular mass to it. So you should expect its average atomic mass to be close to that number. These will still have an effect on your average. So you'll notice it's not going to be exactly 300. It's going to be 300 point something. So when you set this up, you are going to multiply the actual mass by the percentage. But here, the percentage is out of 100%. So you're dividing by 100 or moving 2 places to the left. So when you set this up, it's going to look like this. Now notice I'm not getting rid of any of the zeros because they're still significant. So this is, you're solving for the average atomic mass. So you're going to multiply by each mass and then add them up together. So when you do this, you end up getting 300.25 atomic mass units. And for fun, we can figure out significant figures. So notice it's not exactly 300, 300.25. When you do this first multiplication, you get this number here. Here you get 195, and here you get 90.3. So if I look at this, this number here has how many significant figures? Leading zeros don't count, trailing do. If there's a decimal, that's 3, right? So 3 significant figures. The cutoff is right here. Here you have 4 significant figures on the next one, so that stays as is. Here you also have 4, so technically there would be a 0 there. But if you look at it, your last operation that you're doing is addition. So what do you keep track of?
Decimal places.
Decimal places. First number has how many places after the decimal?
1.
Well, 1, because the cutoff is between the 9 and the 5. So that's 1, 1, 2. Your final answer should be?
1.
1. So what is it?
300.3.
Yep. So that's going to be the average atomic mass of this hypothetical element. This is the number that you'll see in red if this hypothetical element was on the periodic table. So it's a weighted average. Notice the masses are really close to each other, but the percentage makes the difference. It's like your grade. You can have 100 homework points, 100 exam points. Yes, they're points, but they have a different weight to them. Your exam counts more than your
I'm sorry,
homework.
Okay, common.
You have to do the multiplication and addition.
Okay.
So the 299 multiplied by 0.05, then you add it to this product, and then add it to this product. Okay, the next one, you have rubidium. I tell you there's two isotopes. Now this one you have to solve slightly differently. I have rubidium 85. I give you the mass number. Natural abundance. And then I tell you you have rubidium 87. Okay, I don't give you anything about it. And then it says the atomic mass of rubidium is 85.47. You have to figure out the mass of the second isotope. So this is what you're figuring out. Now in this situation, this is your average atomic mass. So in the previous problem, you had to solve for that. Here I give you that. But I don't give you the mass of one of the isotopes. So you're going to solve for that. Now, another thing that I don't give you is the percentage. Can you figure out the percentage? Yes, because I only tell you there's two isotopes. So they have to add up to what? 100%. So what do you get as your
20.83?
28 point, no,
27.
27.
Second guessing.
27.83, yeah. Okay, so that I know. Now you just have to solve for the mass. So you're going to set the equation equal to the average. You know the first isotope. And again, move the decimal 2 places to the left. You don't know the second mass, but you do know its percentage. So I can do that. And then you can just say it's X, Y, it's RB, whatever you want. You're just solving for this. This is what you're solving for. So you can simplify. Notice here you can simplify. Isolate it, move it to that side because you need to isolate this variable. So you'll subtract, and then you can divide by the 0.2783 to figure out X. So it's the same equation, you're just solving for X now. Before I gave you all this information, you had to solve for this one here. So it's just rearranging the equation, that's all you're doing. Here you're going to end up getting the number in 4 significant figures. Yes? Because there's 2 isotopes, right? It's a percentage, so they add up to 100. If the first one is 72.17, the second one has to be 27.83 because you'll subtract from 100. Yes?
So the natural abundance, you always move it over to the left.
Yeah, because it's a percentage out of 100, right? So when you're doing percentages, you always multiply by 100. Here you're doing the opposite. So you divide by 100, and then you end up moving it 2 places to the left. Yeah. Okay, what do you end up getting as your X? 8, 6.9, 2 or what?
92.
So when we're doing this, would we be dividing the 0.2783x by the 24.19, like a whole, like all the decimals?
Yeah.
All of them?
Yeah, you don't wanna round it till the very end.
Okay.
So once you get this product, subtract it, keep that whole entire number, and then when you divide by the 0.2783, you move it onto that side. So just keep it on your calculator, don't just erase it or cut it off in any way. So if you look at this, you have your second isotope, rubidium 87. Not surprising, because notice, if you round that, you do get 87. So here, you're solving for this, for the math. And you can build on this. I could have said 3 isotopes instead of 2, right? So I could give you the information of 3 of them, and you solve for one of the masses.
If there are 3 isotopes, how do you get like the abundance?
I would have to give you 2 out of the 3.
And
Yeah.
how do we find the third one?
Well, you know, there's 3 of them. If you know 2 of them, you can solve for the third one,
Okay.
because they add up to 100. You can have a situation where I don't give you either abundances, but you don't need to worry about that for that class. It's just doing system of equations to actually figure it out, because you know both add up to 100.
So to get the percentage, I'm sure that was your question, but to get the percentage on the second one, we just pretty much subtracted the 100 from the 72.17?
Yeah. Because it's a percentage, it's out of 100%.
Alright.
Yeah. Okay, so we know isotopes, we know protons, neutrons, electrons. Now, when we look at charges, right, you gotta know your names, right, for each group. You have alkali metals, alkaline earth metals. You have the halogens, the noble gases. The charges will come into play in chapter 5. So we're going to see those. You need to know that, okay, group 1 metals like to be +1, group 2 +2, group 3 +3. Then when you get onto this side, the non-metal side, they like to gain electrons. So gain 2, gain 1. They don't like to do anything, because remember, these are the nobility. They're born into it, so they don't have to do anything. So these are the noble gases. You're going to see this in chapter 5, so it's important that you know your charges. Before we start chapter 5, I want to go over a few of the problems, the most missed problems on the exam. So there's still a few scantrons here if you didn't pick up your scantron. You should have your exam, because you never turned that guy in. Now when you're looking at this version, this is version B, which was one color? Pink. If you have the other version, you just have to look for that particular color. It's not going to be number 3 for you. It will be number 8 for you. Okay, so this was one of the main ones, the most missed. If you have questions on ones that I don't cover, and you can't for the life of you figure out how I got it, come to me after class or during my office hours. I have them tomorrow and Mondays, so we can go through it. You look at the first one here, you have 23. What does the capital M stand for?
Megaliters.
Megaliters, right? So I have megaliters, I need to get to nanoliters. Now when you're doing this again, if it's hard for you to go directly from mega to nano, always go to the base unit.
Which S is this one?
This one that I'm showing
Version
is
B.
a B.
Pink one.
You have A, it's number 8 on that. Okay, so what's the multiplier for mega?
10 to the 6.
So 1 megaliter equals 1 times 10 to the 6th liters. I'm going to take it to liters first. Then what's the multiplier for nano?
10 to the negative 9.
Negative 9. So 1 nanoliter, 1 times 10 to the negative 9 liters. Now if you look at your exponent, notice you're dividing. So what do you do to the exponents? So if you don't know what to do with your exponents, you got to review your math. You got to subtract them. So if I do that, what do I get here? 15. Now if I look at this, if I keep the decimal where it is, it's to the 15th power. But notice all the decimals, right, are 2.3. So if I move this here, what happens to the 15th? Turns into 16. That's the answer. You didn't even have to use a calculator if you understood how to do exponents mathematically. You could have put it in your calculator and it would give you the same answer. So notice when I'm writing these, the prefix has a 1 in front of it, then the liters defines the multiplier. So that was one that was missed. Number 6. This was dealing with the density, the floating one. This is number 3 on version 8. So here it says a material will float on a surface if it's less dense than the liquid. That makes sense. Now, given the density of water is 1 gram per milliliter, you have a block of material. So I give you the volume, 1.2 times 10 to the 4th cubic inches, and then I give you the mass, 350 pounds. It says determine the density of the material. So if you're looking at this, you want to compare it to the density of water. Notice its units are grams per milliliter. Now, you can change these to grams per milliliter or change the density of water to pounds per cubic inch. It's up to you how you wanted to do that. You should have gotten the same thing where the density will help you determine if it's going to float or sink. So, what I did was change these. I need to change the cubic inches to cubic centimeters. Why is that okay?
Because then centimeter per milliliter.
Yeah, remember, 1 milliliter equals 1 cubic centimeter. So if I'm able to convert this, whatever number I get is in milliliters anyways. What do I need?